If given 3 moles of hydrogen gas and 2 moles of nitrogen gas, 2 moles of NH3 is formed. What are the limiting and excess reactants? This is the molecular visual of the reaction. In this reaction, the black circles represent nitrogen, the white circles represent hydrogen. When 2 moles of nitrogen gas react with the 3 moles of hydrogen gas, the hydrogen gets used up before the nitrogen gas does. When the reaction is complete, there is still a mole of nitrogen gas remaining. This means the nitrogen gas is the excess reactant and the hydrogen gas is the limiting reactant. This is the balanced equation for the reaction between nitrogen gas and hydrogen gas to form NH3. In this problem, we will start with 2 moles of nitrogen gas and 3 moles of hydrogen gas and determine the limiting and excess reactants through stoichiometry. One way to find the excess and limiting reactants is to start with the nitrogen gas, your 2 moles of nitrogen gas, and converting it to moles of hydrogen gas. You use the ratio from the balanced equation above and multiply the balanced equation and the mole ratio to convert nitrogen gas to hydrogen gas. In this equation, 2 moles of nitrogen gas multiplied by the 3 moles of hydrogen gas equals 6 moles of hydrogen gas. This resulted in 6 moles of hydrogen gas, and we need 3 moles of hydrogen gas to fully react with nitrogen gas. Hydrogen gas is the limiting reactant because we do not have enough to fully react with the 2 moles of nitrogen gas. This makes nitrogen gas the excess reactant. Another way to determine the limiting and excess reactants is to start with your moles of hydrogen gas. We start with our 3 moles of hydrogen gas and use the same ratio from nitrogen gas to hydrogen gas, resulting in 1 mole of nitrogen gas. Since we started with 2 moles, but it only takes 1 mole to react completely with the 3 moles of hydrogen gas, nitrogen gas is our excess reactant and hydrogen gas is our limiting reactant. Now you have seen a visual representation and a stoichiometrical example to find your limiting and excess reactants of the reaction between hydrogen gas and nitrogen gas.
Let me tell you what the experiment is. You saw me lining up all this stuff. This is pretty cool because we get to actually see a reaction go here. I've got a balloon on each of these flasks, and inside the balloon is a small amount of magnesium metal. All right? Now, in the flasks themselves each of these has exactly the same amount of hydrochloric acid, which is HCl aqueous. HCl is actually a gas, but if you dissolve it in water, you get hydrochloric acid, and hydrochloric acid reacts with magnesium, as you'll see. Now, the numbers you see on the fronts of the flasks are the masses of magnesium in each of the flasks. Okay, so we've got no magnesium in this balloon. We got 1/10 of a gram here, 2/10 of a gram, 1/2 a gram, 2 grams, 1. Yeah. Okay. So 0.1, 0.2, 0.51, 1.5, and 2. Helps if you put them in order. All right, so I'll dump the magnesium in the hydrochloric acid. Oh, okay. There's 1/10 of a gram. You can see it going, can't you? Now, what I didn't tell you was the fun part, which is that when magnesium reacts with hydrochloric acid, it makes what? Well, if think about that for a minute. All right. So what's happening here? See if we can figure this thing out. Well, of course, there's no magnesium here. Tenth, 2/10, half, 1, 1 1/2, 2. Now, they're still going a little bit here. We'll let them go. They're not going to go too much longer. And by the way, one of the products of this is hydrogen gas. That's what's in the balloon. Okay? Now, I'll write over here, magnesium plus HCl gives hydrogen plus something, and what would you guess the something is? Magnesium chloride. Now I'm going to put MgCl there, and let's see if we can figure out, we haven't balanced an equation or anything, but we'll see if we can figure out how to balance this equation. It's just about done. Just about done. There's just a little bit of fizz in here. And by the way, these flasks are hotter than blazes. I mean, they are hot. So, we add more and more magnesium, ta-dum, 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 until we get to this point. And then what? Yeah. So, something is limiting the amount of hydrogen that we're having given off here, right? So what do you think it would be? Because we keep adding more and more magnesium. We got plenty of magnesium, don't we? In fact, I can see little flakes of magnesium down here in the flask that have not reacted. Okay? Here too. So the acid, the hydrochloric acid is, and you can see it with your eye, right, is the limiting reactant, isn't it? Because we have used up all of the hydrochloric acid in these 3 balloons, right? And we can't get any more hydrogen gas. Okay? So, divide this in half. Here, from this point on, the limiting reactant is the hydrochloric acid. What about here, 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 and here? The magnesium is the limiting reactant, right? We got plenty of excess hydrochloric acid. In fact, we don't get any here because there's no magnesium. That really limits it. A little bit, a little more, until we get to this point. Now, what point is that? Well, this is 1 gram, and 1 gram of magnesium is 41 millimoles of magnesium, and there's 82 millimoles of hydrochloric acid. 2 to 1, right? So there's twice as much hydrochloric acid as there is magnesium, and that has to be a 2, doesn't it? Right? Is that right? 2H, H2. So there's the balanced equation. 2H, H2, 2Cl, Cl2, 1 magnesium, 1 magnesium. We actually get the stoichiometry from it. This is a balloon graph, right? A balloon graph, a plot of the amount of hydrogen, essentially, that does this thing. All right, now,